Magistri. Today I want to talk about our recent paper, which is a collaboration between the Queensland University of Technology and the University of Bonn. Fruit harvesting in general still relies on human labor, which is raising concern linked to labor shortages, as workers are getting harder and harder to find. So what we want to do in the future is to shift from human harvesting to robotic harvesting, as you can see here in the picture, where we have a robotic arm in front of plants in a vertical farm performing the harvesting operations. So robotic harvesting has the potential to be fully autonomous. This can also enable large-scale vertical farms that we can place close to bigger cities as a way to reduce CO2 emission linked to transport. So to have this fully autonomous robotic harvesting, we need to close the sense, think, act cycle, which is a standard for robotic operation. Specifically to this case, we need to sense the fruit, estimate where they are, how big they are. We need to think about what's the best way to approach the fruit without harming the plants. And finally, we have to perform the harvesting itself. When we look at the challenges from a technical perspective, here I want to show a standard 3D map that you can obtain from an agricultural environment. So when we zoom in around the fruit, sweet peppers in this case, we see that most of the fruits are actually occluded, and the data that we obtain is oftentimes noisy. So our goal in this paper is to develop a harvesting pipeline which is robust to occlusion and can run independently of the end effector design. This means that we can apply it to different fruit without the need to change the vision architecture that we're using. So here we have the full pipeline, and in this talk I want to give you a bit more detail so that we can go from start to end. So I want to first start by defining our working environment. This is a vertical farm that we use for experiments. We were growing tomatoes and strawberries. In front of this vertical farm we have a custom gantry system that allows the robotic arm to move sideways, up and down. The robotic arm is a 6 degree of freedom arm, and then we have an RGBD camera and the end effector to harvest the fruit. In terms of end effector, we have two different designs. We first have a end effector made to harvest strawberries, which need to be cut from the peduncle, and then we have a second effector designed for tomatoes, where we want to firmly grip the fruit itself. And again, we want the same vision system to run with both these end effectors without the need to change our architecture. So the first thing is, of course, to detect fruits in an image. Here we use state-of-the-art instant segmentation network, so I'm not going into details here. But the second thing that we are doing is to estimate for each fruit its 3D shape, complete 3D shape, starting from the noise and partial observation that we've seen before. And together with the 3D shape, we also want to estimate the 6 degree of freedom pose. To do this, we use one of our paper that you can see by scanning this QR code. So given a 3D point cloud or a 3D mesh of our environment, we can estimate for each fruit, again, complete 3D model and a 6 degree of freedom pose. Now the question for us is, given this shape, how we can estimate the best approach direction. So we want to exploit our estimate, both in terms of 3D shape and pose. And to do this, we start by noting that fruits are almost symmetrical around the main axis. This means that we can define multiple grasp direction given a 3D shape and a pose. And among these multiple grasp direction that we want to find the best, as some of them are better than others. Now this can be formalized with a maximization problem, where we want to find the best pose, which is indicated here with this star. The best here means the one that maximizes a function f, and we'll see how we can define it later, that takes an input, a pose, among the set of possible poses that we have defined, which is defined here as tau c. Again, to reiterate, this is our starting situation. We have a fruit. Oftentimes, this fruit is occluded, for example, by a leaf here. And we have our estimate of 3D shape given this partial observation. Now, let's remove the fruit for clarity. And again, we also have the 6 degree of freedom pose and want to exploit these two information to derive the robotic harvesting. So this is a strawberry, so as we've seen before, we want to cut the peduncle, which is on top of the strawberry, so we can move our estimate, and now we can start by saying that this is our grasp point. Note that here the red axis indicates the approach direction, and this specific axis will collide with the leaf, so this is not really one of the possible candidates. But given our understanding of the environment, we actually identify a set of poses which are free of collision that will be possible for harvesting. Now, among this set of poses, which are indicated here from different red arrows, we want to identify one, and this is indicated with this F function here, and in our paper we want to maximize the free space around the robot to avoid as much as possible collision with the environment so that we are not harming the plant itself, and we also want to maximize the distance to the robot workspace limit. Okay, so now that we have our robotic arm, we have estimated our pose, our shape, and we identify our preferred pose to actually grasp the fruit. We can now plan the harvesting and execute it, and for that we use standard solutions like RRT or track IK for the inverse kinematic. Now let's see some results. We have run a bunch of experiments. In the interest of time, we'll just see one of them here. Now we start here with the robot in our left-hand configuration, and you see that it's trying to reach this middle position, avoiding stretching too much to harvesting the fruit. As baseline, we compute different, we use different approaches, both learning-based and non-learning-based. As you can see here from our success rate graph, our approach outperforms the baseline both on strawberries and on tomatoes. To conclude, I hope that I show you how we can improve robotic harvesting with 3D shape completion, and we also show that our approach can be adaptable to different end effector without changing the overall perception system. If you want to know more details, scan out this QR code, and thank you for your attention.